Next, we have Mahdi from Qualcomm. Dr. Mahdi is an assistant professor of the School of Computing at University of Utah. He received his PhD degree from the University of Rochester, USA in 2016 in electrical and computer engineering. Currently, he leads the Unconventional Computer Architecture Laboratory, UCAL, at School of Computing, University of Utah. Recently, his research interests have included energy-efficient architectures, low-power memory systems, and the application of emerging memory technologies to computer systems. Professor Nardi's research has been recognized by two IEEE Micro Top Pick Awards, an HPCA 2016 Distinguished Paper, and a Samsung Best Paper Award. We welcome Mahdi, Professor Mahdi to present his talk. Please feel free to share.
Good evening, everyone. Thanks for the introduction. Can you see my screen?
Yeah, I think it's still popping up if you're sharing your screen. Yeah, it has popped up now. Thank you so much.
Yeah, thank you. So I have to mention that everything is to my research at the university, an assistant professor there. So today I'm going to talk about a little bit about data processing and what we have done recently about data processing and memory bandwidth optimization. So there's no need actually to mention that data processing is on a huge rise and has been actually gaining a lot of attention by designers and business. Just a few examples, if you just look at supermarkets like Walmart, you see that we are producing a huge amount of data every minute, so petabytes per hour from Walmart. Or in the category of scientific applications or telescope, we are collecting hundreds of petabytes, and we have collected exabytes of data for large Hadron Collider. So this huge amount of data is collected every day, every minute. And of course, we need to process this collected data. And for that, there are two very interesting aspects that are created for a lot of people. One is money-wise. It is actually creating a huge market. And a lot of people are attracted towards data processing specifically for this reason. And of course, for architects and system designers, there is another aspect that is very critical and important and is gaining attention, is now to store, to process, and to move this amount of data, we need to design architectures and systems that can efficiently handle this huge amount of data. And as mentioned in the previous talk, moving such huge amount of data is going to be very costly and is going to be a huge factor for future data processing. If you just look at a single example, by 2030, the required bandwidth for fully autonomous self-driving car is expected to reach near 1 terabyte per second. And this is huge bandwidth that we have to provide. As architect, we have to think about different techniques and novel ideas to provide such bandwidth and make it efficient, of course. So if you look at research that has been basically pursued by a lot of researchers around the world, we see that there are different components that have been proposed at different levels of the compute stack, mostly at the algorithm and data structures. We are seeing some breakthroughs for different applications. For unsupervised learning, neural networks, point cloud processing, self-driving cars. These are just a few examples to show that we have progressed significantly at the algorithmic side of basically system designs and handling such a huge amount of data. But when we look at the architectures that we've designed, it's been very limited. Most recently, we've designed architectures, accelerators for CNN, but we have to go beyond that. And in this talk, I'm going to just give an overview of research that we have done and basically what we can do in future. What we think is that what has been done in terms of hardware and architecture is not enough, and we need to basically invest in this sector more. And of course, we have to focus on a holistic optimization, as was mentioned in the previous talks today. Holistic approach for optimizing the whole system for efficiently process this huge amount of data. So co-design is one solution, definitely. But the key message from this talk would be basically that we need to work on both high level and low level and combine together to come up with efficient solutions. So we believe at the University of Utah, we believe in this famous quote by Alan Kay that people who are really serious about software should make their own hardware. And this has been our motto in recent years and designing unconventional computer architectures for data processing. If I just look at my research, this is just a simple overview, very simplified overview of my research over the past decade or so regarding data processing. We've been focusing on data processing at different levels. From top, we've been designing algorithms and resource-aware data structures. Now that we basically have a good understanding of what's happening when we move data in the system at the very low level, or memory bandwidth requirements and memory capacity requirements, can we just come up with data structures that are useful, or algorithms that are useful and efficient based on that knowledge for the entire system, for the end-to-end performance of applications. Another category of optimizations that we've been looking at has been cost-efficient data codes and encoding techniques that can basically give you better memory bandwidth utilization, energy efficiency, and low power for processing. Another category would be has been energy efficient interfaces, more specifically memory interface and moving data between the processing components and the memory. And of course, we've been one of the first who looked into in-situ computation, which takes a step further than in-memory processing or processing in memory, and going into the memory arrays and doing in-situ computation inside the memory arrays. Of course, we started with basically this sort of computation with analog computation, sometimes mixed with digital computation for dot product engines, and of course, clustering engines. And more recently, we've been looking at other computations that can be done digitally, not analog, because analog, at the end of the day, is going to be difficult for different reasons. Digitally at the memory, inside the memory arrays, with some modification to do digital computation and enable some important applications using in-situ computation. In the interest of time, I'm just going to summarize two ideas, basically two main ideas, very recent ideas that we had at the two extremes of this spectrum. At the very top, we are going to see some of the highlights of our recent work on geometric arrays for point cloud processing. It's a data structure fully in software, but we designed this data structure with the knowledge of the memory bandwidth and optimize it for the low-level resource management, where we observe a huge benefit of such redesigning the data structure for point cloud processing. And at the very bottom, we have compute-capable memory arrays, basically changing the array structure for doing some specific computation for a large class of, an important class of data processing. Ranking engine that is used for sorting and ranking data inside memory without any data movement, without moving raw data, because as we know, data movement has been very expensive. So optimizing data movement has been at the heart of all these optimizations. So that's the key problem that we are trying to solve across all of these optimizations that we have done. So let's start with geometric arrays for point cloud processing. As I mentioned, this is an efficient data structure designed for point cloud processing. But before that, what is point cloud? I'm pretty sure many of you are pretty familiar with point cloud processing. This is just an overview of point cloud and what kind of data we are encountering when we are doing point cloud processing. Point cloud processing is a rising field in 3D modeling, and it is actually used for different applications. If you look around, we are seeing today, we are seeing a lot of sources that can generate point clouds, such as medical imaging devices, robotics, and automotives. Computer graphics are generating point cloud these days mostly. And if you look at tablets and portable devices, they've been enabled with these LiDAR sensors. And this is actually promising in the case of we're going to have a lot of these point cloud data being generated by these handheld devices and portable devices. In the future, we're going to see more point clouds. And these are the sources of point cloud. And of course, all of these are going to generate point clouds. And then this point cloud is a kind of data that is being processed by a lot of other applications for useful, applications such as manufacturing, precision medicine, virtual and augmented realities, and of course, deep learning is going to make sense of these points that have been collected by LiDAR sensors or generated from different sources that we have. And but when we look at point cloud memory requirements as a memory architect, this is the first thing that I would think when looking at the point cloud. I see that there is a big challenge with this point cloud, and it just reminds me of video data that we had decades ago. Point cloud data size is increasing significantly, and this is mainly because of two main reasons. And one is basically there is an increasing need for point cloud streaming for a lot of these applications because we want to get higher quality output of these applications. And the other reason is that higher resolution point clouds are coming. So when we look at point cloud streaming, unlike still point clouds frames where we had like special samples that are collected from an environment or generated for a model, now we are going to increase the number of samples because we add another dimension, which is time. We are adding another dimension to samples, and more points are sampled in time and space. And this is why the size of point clouds is increasing significantly. And when we look at the size of each frame of the sampled point cloud, we see that it is increasing because high quality is required for a lot of these applications. If you look at, for example, this is the data that is basically released by some standards like MPEG, which is active in the area of point cloud. If you look at a single human body, the number of points that we have today, typically for a reasonable quality, we have 100,000 points per human body. And for future applications at higher quality, this is going to be increased by 10 to 100x in near future. And keep in mind that this is for a single human body. If you want to model a crowd, then of course this multiplies. And because of these two main reasons, we are expecting the amount of the data for point clouds in near future increase significantly. And now that we are talking about the huge amount of data, we know that in a lot of these cases and a lot of SOCs and computer systems that we have, this amount of data doesn't fit in the cache, and we have to go off chip, and memory is going to be at the center of these applications for any optimizations. And moving this data even on chip or off chip is going to be a significant problem. So what we did is that we looked into this area, and then we first tried to understand what are the possible representations for such data. And we started with that, and we looked at point cloud data representations. The problem is that this is the problem after we looked at the existing methods for representing data, which is actually this the structures that we are using for representing point clouds today are not holding any geometric information relationship among points, or they just they can only hold a limited amount of geometric information among points. And this is pretty important aspects of representing point clouds, because when it comes to processing points, we want to understand the relationship between that point and other points, which ones are closer, which ones are basically farthest, and there are many other applications you can actually look into when it comes to processing such data. So in general, we have two types of representations for point clouds. One is we categorize it as unstructured points, simply an array or just a file of dumping all the data into an array of 5. And these are unordered, unstructured. We just dump the whole data in that array. And each element of that array will be basically a tuple comprising coordinates and attributes. In this example, you can see we have XYZ coordinates and attributes are RGB. The attributes could be basically more or less than this, depending upon what type of application you're dealing with. And then the other type is structure point. Of course, we can actually try to organize these points in a tree or graph structure. Of course, that requires more data just to hold the relationship between these links and basically the relationship between these points in that structure. And so that consumes more memory and requires more metadata to be stored together with the points. But if I just want to summarize the pros and cons of these two types of representations, so unstructured points, a simple array, will be nice for searching because it has a lot of special locality. When you access a part of this array, of course, there will be special locality that can fetch the surrounding points. And if you need in future to access those points, you can take advantage of that special locality. Smaller memory footprint, we are just storing points. We are not adding any special metadata, but it suffers from slow lookup, which is actually one of the basic and important operations for point cloud processing. But when we look at the structure points, it needs pointer chasing in a lot of cases because we want to keep the relationship if we want to optimize memory. So pointer chasing is one of the problems, and pointer chasing for a huge amount of data, more specifically when data doesn't fit in cache and you have to go to the memory, is going to be very expensive and you need to move a lot of data. And it has diverse impact on bandwidth efficiency. And it needs a larger memory footprint because of the metadata that we add to the points. But in terms of lookup, which is the basic operation for point cloud processing, is going to be faster than linear scan. Now we have these two types of representation. One point to add on top of this, you may think that structure points is actually holding the geometric relationship among the points, but when it comes to, let me just get my pointer, sorry, laser point, okay. Oops. I'm assuming you can see my cursor now. When it comes to geometric relationship among these points, keep in mind that even at the leaves, if you have 2 points close to each other, we don't have any exact or accurate or useful information about the geometry relationship of these 2 points. For example, these 2 points are not necessarily closer to these 2 other points. If you have in a completely different branch of this tree 2 points, it doesn't mean that the ones that are below the same node are basically closer to each other. And that makes the whole process of finding nearest neighbor or farthest point from a target point very challenging. So now the question is, what can we do? Probably a hybrid model or something in between could be very useful. And this is what we started with. And we don't think that this is the ultimate and the best solution. And of course, we can come up with better solutions, but this has shown a significant improvement in terms of memory bandwidth. And in some cases, compression-wise, it is actually saving capacity. And in terms of speed, we are gaining significant improvement on real machines when we test it compared to existing state-of-the-art representations. The key idea is just to preserve the geometry of points along individual axes within multiple arrays. So instead of using a huge or basically a deep hierarchy of pointer chasing to reach a leaf or a point, we limit the number of indirections to only 2. So basically, we are using multiple arrays to take advantage of special locality. At the same time, we want to take advantage of basically linking across different axes. And because we have 3 axes, we limit the number of pointer chasing to 2 levels. So we define 5 arrays on top of the RGB values, and these 5 arrays are going to hold the geometry. So here's an example of a query. We're looking for a point 137, 95, 61. So XYZ. These are the target XYZ for a real example. So what we need to do, it's pretty similar to, it's a lot different from CSR format that is used for a sparse matrix representation, but it is pretty similar in some aspects to those to CSR format for representing sparse matrices. So what we do is first we take the target X and find it in the X pointers, and using X pointers we find an index to the Y arrays. So keep in mind that when we reach the point 137 in the X index, we have 2 pointers, 3 and 5, the next one, that is actually indicating the range where we can find the Y index for the Y pointer. And then we can go to the index that is indicated by X pointer in the Y array, find the next coordinate, and then we can keep going down all the way to the point that we want. So using 2 indirections only, we can reach a point. Now, the interesting part is that when it comes to searching for nearest neighbor, keep in mind that when you access an element of this array, the neighboring points are going to be fetched to the memory. And this nice structure can take a significant advantage of the special locality for finding the neighboring nodes if you need to search for those nodes. And in a lot of cases, we found that this is super useful for basic operations when it comes to point cloud processing.
Mahdi, I just wanted to take a moment to say that if you're using your mouse, it's not visible yet.
Okay. Can you see my mouse now?
Not yet.
No.
How about this? The laser pointer,
yes.
can you see?
Yes. Yes.
Okay, sorry about that. Okay, right. So yeah, so this is the process for accessing basically a simple lookup for a point in the point cloud. Now this is a basic operation, and we went beyond this. And in this talk, in the interest of time, I'm going to skip that part. The other operations that we have done, like merging the two point clouds and a couple of other operations like projections and different things that we have done. And because lookup is the key operation for a lot of these point cloud processing, this was as an example. Now let's see what we can do with this lookup operation or this structure. So one thing we can do is basically we focused on point cloud compression, which is actually under standardization with the 2 different standards. MPEG is one of those. We pick MPEG standard and the code, and we try to optimize that using point cloud. Keep in mind that in this existing methods that are used for point cloud processing, they're using octree or KD tree structure, which is a tree structure basically. So let's look at one application here. We are focusing on point motion estimation, and we try to use G-arrays for point motion estimation. If you're not familiar with point motion, basically motion estimation, if you have 2 frames, either video or point cloud, frame 1 and 2, let's say that we have sent the frame 1 to the destination. Now when we want to send frame 2 to the destination, we don't have to encode the entire thing. So what we can do is that we can find the differences between the 2 frames and send the difference between the 2 frames. Now the receiver can basically take the difference, and by just setting the frame 1 as a reference, can reproduce frame 2. So this is the goal. So what we can do, this is just an example, 2 frames of sequence, point cloud sequence. When we look at these 2 point clouds, we see that some points are exactly matched and they are removed from the entire difference frame that you can see. Some points are not, the color is a bit different, and some points are completely missing. and we have to send them. So this is what happens for a point cloud processing. What we did on top of this is that first we found the difference, and then we did this difference computation based on clustering first, which means that for both frame 1 and 2, we did the clustering. You can take your own clustering algorithm, but for this purpose, we use k-means. And we limit the number of iterations to find different clusters of these points, starting from 8 coordinates of the space. We set the centroids and then found the different clusters. Now what we do is that we try to find the motion vectors for different clusters. So for example, we have this blue cluster over here, and then there's another blue cluster here. Between the two centroids, we find the motion vector. And this gives us a coarse-grained motion vector. Now, when it comes to encoding and finding the differences for these two clusters, what we do is that from frame 2, we want to find those points that are within this cluster blue in frame 1. Sometimes we have some corresponding points, sometimes we don't, and we have to send a point. And sometimes the color is a little bit different, and we have to send a color difference. So here's when the data structure that we propose comes into play. We make this whole process of finding points super fast and very efficient. Keep in mind that this idea is not implemented in the original code for MPEG point cloud GPCC or MPEG geometric point cloud compression. We enabled this using this structure, and then later you see that we can actually we could improve quality of video compression by just enabling this feature for video process, for point cloud processing. So these are the original blocks, the gray blocks that you can see on the right. These are the original blocks that are in MPEG GPCC, special special encoder. This is just based on special encoder. No temporal encoder exists there. So what we did is that we added these proposed blocks that can do point clustering, point moisture estimation, as I mentioned, and then residuals. So then we have the residuals, some of the points that have to be transferred. We send these residuals to the special encoder and send it to the destination. We tried this on a real machine. These are not simulations. These are just a library that we developed and used for processing, and we use baseline compression, as I mentioned, and MPEG GPCC. And we consider different metrics to measure performance of this proposed data structure and encoding mechanism. For output quality, we are using PSNR, compression ratio, and memory requirement and execution time. These are the things that we consider for performance evaluation. And we focused on input sets, mostly generated by computer for compression, but it turns out that for LiDAR sequences, we are actually better than this. And I added some extra data on top of that to this presentation. But in the original paper, we don't have LiDAR. And the reason is because LiDAR has fixed 1 or 2 fixed dimensions. And because of that, it turns out that the data structure that we propose is going to be super efficient. So in terms of speed up for different operations, such as merging point clouds, nearest neighbor search, projection, these are 3 different basically operations for point clouds that I didn't discuss in this presentation. I'm not going to talk about them. These are just merging, except the nearest neighbor search. And then this compression is just GPCC that we talked. We noticed that this data structure can enable significant speed up for processing points. These are the speed ups that we gain for the input workloads that we discussed. And the speed up is significant. And we propose this. We think this data structure can be even better than this, but the results is very promising. Not only speed up, we can actually improve memory capacity and memory consumption is another thing that we can actually achieve using this data structure. About 5% memory saving over octree's data structure. And the reason is because we don't need much metadata, And at the same time, we have an opportunity for compressing points along the axes. So for example, imagine that you have 2 points with the same x. They are sharing x. And that actually results in compressing the data structure. And it turns out that actually we can actually improve both compression ratio and quality. This is very rare in the case of video processing or point cloud processing. The reason is because now that we have this data structure, we can improve speed, time. At the same time, we can actually enable other capabilities such as looking for points in the data structure and enabling different novel temporal encoding mechanisms to improve quality of compression. So this was a summary of one of this high-level basically optimizations that we considered recently in terms of developing a new data structure at a very high level. This is completely software level. And of course, this creates a lot of opportunities for designing, for example, designing a prefetcher based on this data structure to gain further improvement in terms of energy and speed up when it comes to real applications. So this is one example, high-level optimizations that we have considered recently. Now I'm going to switch gear and talk about an optimization that is at the extreme end of this spectrum of data processing optimization, which is considering a bitwise data processing approach to large-scale data ranking inside memory arrays. And we are doing some in-situ computation. We specifically picked membristic data structure to gain basically to enable very large-scale data processing for future applications. So what is data ranking? So when I say data ranking, basically it means that you have a list of, say, numbers and you want to sort them or rank them, find the second, the first, the second, the third, or the nth smallest number in your list. So this is what basically I mean by data ranking here. And it found a lot of applications in different domains like database processing, clustering, graph processing, VLSI layout, and genome analysis. And if you look at these applications, you see that a lot of different kernels that have been basically exploited by these applications, like in-memory KV, different kinds of Dijkstra, Crucible, A-star search, are used for these different applications. At the heart of all of these, we have data ranking, or basically we need to sort data. So these are just a number. Of course, sorting data itself is going to be used for other, maybe used for other optimization techniques that I'm not going to talk about it here. But when we look at what we've done, what has been done before our work is that we have prior work on data ranking. Almost every decade, we've seen a new algorithm or basically something new in the era of basically sorting data. So at some point, we had basically, before some point, we had notable software solutions that could actually improve the performance of sorting and ranking data significantly, such as merge sort, radix sort, and so on and so forth. And then at some point that all software solutions were saturated, people thought about notable hardware solutions, such as multi-core implementation for SIMD, GPU, ASIC, and so on and so forth. So we've been looking at basically different techniques for improving data ranking in the past. But we did an analysis to understand what is at the heart of all these sorting and ranking data. And we noticed that memory bandwidth plays a critical role in data ranking. Here is an example, and this is basically our base observation here. So we are looking at 3 different systems. 2 of them are realistic. The last one is unrealistic and ideal memory system. And these are, again, with this experiment is centered on different memory systems for data ranking. Off-chip, we have in-package high bandwidth memory and unlimited memory. You can see from left to right, basically, As you increase the memory bandwidth, the performance of these algorithms increases significantly. Then we wanted to understand what's happening and what is the bottleneck in terms of bandwidth bottleneck for this algorithm. We noticed that there are different applications that are using the sort or ranking algorithms. For these existing solutions, we have unordered data. We have to sort them first. Keep in mind that when we sort with this conventional techniques, what happens is that we are just reordering data in memory with different mechanisms, software, hardware, in-memory techniques, different mechanism, and we sort them with respect to memory addresses, or basically index-based ordering. And then what happens is that the user application provides an index to this sorted data, and then we get the data. So basically, user wants to get the end element of this sorted data and then get that data. So we thought we can actually change this mechanism and remove some of the steps from this whole process to make it much faster. Or basically, we wanted to remove the sorting part, which takes significant amount of bandwidth, and it imposes a huge amount of data movement in the entire system. So what we do is that we thought, what if we didn't have to provide index to get data from the user application? What if we had a memory system that can hold this unordered data inside it and then provides both data and index to the user application? Now it's up to user to use this data. And for a lot of these applications, we noticed that this solution works, and it's just fine, and it's just like the original algorithm we have. So basically, the key idea is just to remove index accessing. And we noticed that by removing this step, we could actually save huge amount of bandwidth utilization, bandwidth requirement, and energy consumption, and of course, time. So we, of course, implementing such technique requires innovation of both algorithm, data structure, and hardware. So we first tried to propose an algorithm for such operation, and we invented two basic rules. We noticed we tried to organize all this values and data in the memory in a structure that you see on the right-hand side. The numbers are 4, 1.75, and so on and so forth. We just organized in a 2D array, which is actually pretty much the conventional array structure where we store data. And then we invented two simple rules for processing data. Keep in mind that I'm not doing analog computation. I'm just trying to do some accesses. And the key operation here is just to access or select data horizontally and vertically. This is the main modification that we apply to the conventional data arrays to enable such computation. So the first rule is just to search for all zeros, and for those ones column-wise. So you go column-wise from left to right, search for zeros, and then for those rows that have ones, we exclude them from data. So basically, these are the two rules that we apply. Here's an example. Starting from the left-hand side column, I'm searching for zeros. I have 2 ones. I'm going to exclude these 2 in the next step. I just need to mark these 2 rows and move on to the next column. Search for zeros and ones. I don't have a mix, so I'm not doing anything here. Search for ones. I have all ones, no zeros, so I'm not going to do anything in this step. The next column, I search for ones. I found one row that has 1, so I'm going to exclude that. And then the last row, the last column, I'm going to search for 1 and exclude that. And then ultimately, I find the minimum value. So this algorithm works for unsigned fixed points. And interestingly, with some modification, we can actually get this to work for both signed fixed point and floating point. So for signed fixed
Professor,
point,
I just want to give a 5-minute time check.
Sure, I'm going to wrap up and skip a lot of some of the details and jump into the results and open for Q&A. So the point is that this algorithm in some modification works for signed fixed point. The point is that when we know these are fixed point numbers, just the most significant bit is going to be, bit position is going to be treated differently. And after that, if necessary, we change searching for ones. And so this is the only thing that the only modification which is trivial, we can actually make to the algorithm that works. And interestingly, we found that the same algorithm works for floating point. And the reason is that, first of all, the data structure for floating point, the representation is sign magnitude. Of course, for magnitude, we have exponent and mantissa. The way that we basically organize exponent and mantissa is that from left to right, the significance of this bit positions are monotonically decreasing. And this enables this algorithm to just be fine and do the minimum or maximum value for this data representations too. So the other thing is that now that we have this algorithm, the question is how are we going to implement it? Keep in mind that if you just implement this algorithm using a von Neumann machine, where you have the processing elements separated from memory, this is going to be really bad, very slow, inefficient, and it's going to basically create a lot of data movement. So don't do this at all. So this is going to be even worse than whatever we have today. But we noticed that if you just combine both computation and memory requirements and do the computation in situ, then what happens is that we can actually gain a lot from this type of algorithm. So just to summarize, we changed the algorithm for finding minimum or maximum, and then we implemented this inside memory array. And then we looked at different architectures and data and basically data arrays that can be used for such operation. We noticed that there are two technologies. We found two. You can find more probably. We found two technologies that can be used for such algorithm. And the reason is because we were looking for a data structure or a 2D array structure where you can actually do the selection bitwise or column-wise and basically search column-wise and select row-wise. For example, EDRAM that has two different networks for writing and reading can be a candidate for such algorithm. Another candidate could be RRAM cell, which can actually be accessed row-wise or column-wise. So because we wanted to support large-scale data processing, we focused on RRAM cell. So there are a lot of details that I'm going to skip here. Just to get this idea to work for a mechanism, one optimization and one design consideration is that the network that is connecting many of these arrays in a large scale has to generate an index. And we basically designed a novel indexing mechanism that can be used using this H tree that is connecting these arrays to generate an index for the minimum or maximum value inside the arrays. I'm going to skip these slides and jump to some of the results. So for experiments, we evaluated the system for an architecture in simulation. We did circuit simulations, programming model, and different workloads. And we noticed that we can actually, using this mechanism, we can actually significantly improve the performance of sorting data, huge amount of data, significantly, 2 orders of magnitude in a lot of cases. For merging, when you have two different sets of data, you want to merge them in database application, again, we gain significantly. And for ranking data, which is used by some algorithms in network, IP search, or finding malicious, basically attacks for networks, we noticed that this technique can significantly improve performance. And energy-wise, because we are eliminating a huge amount of data movement in the system, we can save, in simulation, of course, 90% of the energy consumption when it comes to these algorithms and applications. So in summary, from this talk, I would say for future data processing applications where we need to gain 2-3 folds of basically energy efficiency or performance or basically power reduction, we need a combination of optimization at the very high level, at the very low level, or co-design optimization that can merge all these optimization across the compute stack. Thank you.
Thank you, Professor Mahdi. That was really interesting talk and highlights a lot of concerns which we face with memory optimizations, especially when it comes to large-scale networks.